Professor, you're muted.
Welcome to class, everybody, and thanks for letting me know I was muted. I want to thank you for attending, and you've all got your test twos scanned and uploaded. I have been absolutely buried between fixing my computer and right getting the late video up and then all this grading. So I haven't had a chance to put the N Choose R short video up yet. I will do that um, as soon as possible, but it's not critical. It's a topic that I think you'll find interesting. But right now we're going to move on tonight to our proof by mathematical induction. So our goals tonight, let me go on and pin this. Congratulations to the people that did very well on the test. We had some very high scores. We are still going to be in section 5.1 just for a minute because we have a few thoughts still about summation and product notation that we need to discuss that will help prepare us for our proofs by mathematical induction. And then we will dive into section 5.2, which is, well, first we're going to talk about statements concerning an integer n. What does that even mean? And then we will then discuss what's called the weak principle of mathematical induction. It's sort of a misnomer because even though it's the weak principle of mathematical induction, it's just as powerful as the strong principle, just sometimes less convenient for certain kinds of statements that we want to prove. Then we're going to look at useful formulas. We're probably just going to get to one of them tonight, and then we'll look at some more of them on Wednesday night. But useful formulas that we can prove. Using proof by mathematical induction. So we'll do our first proof by mathematical induction tonight. And hopefully by the end of the evening, everybody in here will understand the concept behind mathematical induction and what does this really mean. And we'll also look at some applications of this formula. And I hope that I'll have time to tell you a story about Gauss. There's an interesting true story about the mathematician Gauss that has to do with applications of the formula. So in the meantime, let's do a little think now to warm up. How could you write each of these using a single summation or product symbol? So we're going to practice a particular skill that will help us in our proofs by induction. Okay. So the first statement looks like this. A, the sum from I equals 1 to k of the expression 3 to the I, whole thing minus 1, plus the sum from I equals k plus 1 to k plus 1 of the same expression, 3 to the I minus 1. I'd like you to think about how you could write this sum of two summations as a single summation. And then the product example goes like this. the product from I equals 0 to 6 of I squared, 2 to the I, times the product from I equals 7 to 7 of 2 to the I. And this game of taking two sums and writing them as a single sum, or two products and writing them as a single product, is a game we can play in two directions. One direction is to consolidate it and write it as a single sum or product. But the other direction would be to break off a term. So that's our second think now problem. Can you break off the last term in each expression? Question? Question? So this first one, A, is the sum from I equals 1 to k plus 1 of I squared. And the second one, B, is the product from I equals 1 to k plus 1 of the expression 1 over I, or the reciprocal of I. So any ideas about how we could write this first sum of sums as a single summation?
It's P plus 1.
Yeah, from I equals 1 all the way up to k plus 1, because you see k plus 1 picks up where the k left off, right? It picks up at the next integer value. So let's just think about what this really means so that we can understand how we could write it in a different way, but say the same thing. Question?
Oh, sorry, I was unmuted.
Oh, okay. Thanks. So here are think now solutions. One A. Okay. So let's just notice what each sum means when we write, this sum plus that sum. Well, when I is 1, we just put a 1 in there where the exponent is. So the first term is 3 to the 1 minus 1. And then it's a sum, so of course there's a plus. And then we increment I to 2, right? That's the way this works. We increment the indexing variable I. So now it's 2, so we plug in a 2 everywhere we see an I, and we've got 3 squared minus 1. And you keep going, dot, 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 until we get to the last value, the upper limit of the indexing variable, which is k. So when I is equal to k, we just plug the k in where the I is, and we've got 3 to the k minus 1. Whereas this sum, so this was the sum from I equals 1 to k of 3i minus 1. Okay, that was that sum. Sorry, that's too small, but oh well. Whereas the other sum, the sum from I equals k plus 1 to k plus 1 of 3 to the I minus 1 is just a single term. It's just the term when I is k plus 1, because the lower limit and upper limit of this sum are the same. And if you've done any of the homework, you've seen that that's possible. So this quote unquote sum, it's not really a sum, it's just that single term. So as a single summation, we can just put those together, right? And it would be the sum from I equals 1 all the way up to k plus 1 of 3 to the I minus 1. So that's the answer to our first think now, because now we've written it as a single sum. Let's look at the next problem. We're asked to write that product as a single product, right? Well, I think you get the drift. So let's just go right to the answer. As a single product, how would we write this product of two products? Anybody?
Would be the pi symbol from 0 to 7 of 2i.
It'll be the pi symbol from I equals 0 to 7 of 2 to the I.
Yeah.
Yep, it's exactly right. Nice job. Everybody see that? Because, of course, you know, the 7 picks up right after the 6. So you can think of it as a continuous product. So if we want to play the game in the other direction, we can break off the last term in an expression. So here is an expression where we're being asked to break off the last term. Okay, so let's see if we can do that. So for 2, well, the last term in the expression is the term where the indexing variable is taking on that upper limit value. So the last term in this sum would be I raised to the k plus 1. So that's what we're going to be breaking off. What's the integer right before the k plus 1?
K.
Uh-huh. So if we think about it, breaking off the last term, we can just write this sum from I equals 1 to k plus 1 of I squared as equal to a sum from I equals 1 to the integer before k plus 1, which of course is k, of I squared, plus, well, the last term is when I is equal to k plus 1, and k plus 1 is the both lower and upper bound, and it's of the expression I squared. So that's just a single term. So we're playing the game, you know, in the other direction. If we want to play the product game in that other direction, say we've got the product from I equals 1 to k plus 1 of the expression 1 over I, well, again, the term right before, the integer right before k plus 1 is k, right? So here we just say, hey, it's the product from I equals 1 to k of 1 over I times, got to remember to put times because it's a product, the product from I equals k plus 1 to k plus 1 of 1 over I. So we get two different answers, but it's the same kind of a game. So the thing to understand, and in WebAssign, you may decide to do this, this term can just be evaluated. It's just the single term when I is equal to k plus 1. So it would be the quantity k plus 1 squared. You know, that would be another way to write this term without using the symbol that is the summation symbol. And of course, this term is simply the term 1 over k plus 1. You know, it's a product, but it's not being multiplied by anything. It just sits there as the only factor when the lower and upper bounds of the product are the same. So Any questions? But again, I just want to put in a plug for the CNR video. It will go up as soon as I can. I've just been absolutely buried. But it is a topic that I do want to give you a video on. The N-Choose-R video, still coming. Just keep an eye out for an announcement through Blackboard. And as soon as I can get it up, I'll send around an announcement. Meanwhile, you've got homework 5-1. You may have finished that already, but I did give you a couple of extra days. Normally it's due on Monday at midnight, but you've got until Wednesday at midnight. And homework 5-2 and the next special homework, I'll get them out to you as soon as possible. And now we're ready to start section 5-2, which is proof using the principle of mathematical induction. So I want to just ask a few questions to gear up to this discussion. We're talking about a principle of mathematical induction. So my first question to you is this: what is a principle in mathematics? What is a principle in mathematics? Does anybody know? Or do you have any kind of idea or intuition about what that word might mean in mathematics? I'll tell you. It's a statement that's so obvious that we accept it as being true without even proving it. I'll give you an example. Sometimes we call them axioms. Here's an axiom or a principle that you know about, and I'm sure it won't sound at all strange. In geometry, if we have 2 points, we know those 2 points determine a line. Everybody knows that. If you have 2 points, you can connect those points with a line. And that's a principle of geometry. It's self-evident. It's not something that we prove. And, like I said, it's called an axiom, but sometimes these ideas are called principles. So the answer to my question, what is a principle in mathematics, is it is a statement that is so self-evident it is taken as being true without proof. Now, it turns out that the principle of mathematical induction is quite intuitive. I'd like to draw you my kind of famous picture that I draw. This is what the principle of mathematical induction says. It says, if you know something is true at some bottom, actually, before I do this, let's discuss one more thing, and then I'll draw the picture. So I'm just realizing there's another question we need to address before I draw that. The other question I want to ask you is this: what is a statement concerning an integer n? This phrase, a statement concerning an integer n. It's the kind of thing that is easier understood through examples than a formal definition. When we were starting to talk about contradictions and what would constitute a proof by contradiction, I gave you some examples of contradictions, and then that made it a little easier to understand what it means to say, hey, that's a contradiction. For example, 0 equals 1. That's impossible. An integer is both even and odd. No can do, right? A number is both rational and irrational. So those were sort of ways for you to understand contradiction without me trying to formally prove it. The formal proof is it's a statement that's always false. Well, same here. What is a statement concerning an integer n? To answer that, I'd like to just look at a few examples of statements concerning an integer n that you're going to find familiar. So let's look at a few examples. Or at least they'll seem reasonable, one hopes. Okay, example 1. Here's a statement concerning an integer n. The sum of the first n positive even numbers is given by the formula n plus 1 times n. In other words, if we write the sum from I equals 1 to n of the expression 2i, these are even numbers. When I is 1, and we plug in 1 here, 2 times 1 is 2. The first positive even number is in fact 2. Then when we plug in I equals 2, we get 4. 2 times 2 is 4. When we plug in 3, we get the next even number, you see? So this is an expression for the sum of the first n positive even numbers. So the claim is that that sum, no matter how large n gets, is always going to be given by this formula, where this n is the same as that n. Okay? And this is for n greater than or equal to 1. It doesn't make sense for the upper limit of a sum to be smaller than the lower limit. It can be equal to it, though. Here's another statement concerning an integer n that you've probably heard about. The sum of the interior angle measures in a convex polygon. I'll tell you what a convex polygon is in a minute, but just think triangle, square, hexagon, pentagon, octagon, okay. The sum of the interior angle measures in a convex polygon having n sides is given by this formula. A lot of times these are formula type things. 180 degrees times n minus 2. Now, let's just check this so that you know what I'm talking about. When I'm talking about a polygon, I'm talking about a closed figure like a triangle, like when n is 3. You know, when you have 3 sides, you've got a triangle. Do you remember from high school how many degrees are inside a triangle? You know, the inside angle measures. Do you remember how many degrees that is? Anybody?
Is each angle 60?
Well, it could be if it's an equilateral or or equiangular triangle. If it's equilateral, it's also equiangular. So yeah, they can be 60, 60, 60. So what do those add up to then?
Oh, 180.
Yep, it's always going to be 180, whether it's equiangular or not. And in fact, when we check this formula, let's just check the formula. N is 3 because we have 3 sides to this. 180 degrees times 3 minus 2 is, of course, 180 degrees times 1, and that's 180 degrees. So it works for a triangle. Do you remember the sum of the interior angle measures of a quadrilateral from high school geometry? This is when n is 4. We have 4 sides, so it's a quadrilateral. Well, the way to learn it is to know that there's 180 degrees inside a triangle, and then you can take a line and connect the opposite vertices of this quadrilateral and it makes 2 triangles, and each triangle has 180 degrees inside of it. So the total would be twice that. And our formula confirms that. It's 180 degrees times, well, n is 4, so 4 minus 2, or 360 degrees. So in case you didn't remember, the sum of the interior angles in a quadrilateral is 360 degrees. And I mean, this keeps working no matter how large the quadrilateral is. Now this convex part is just saying that the shape of this doesn't have parts that stick out. I'll show you a polygon that's not convex. A 5-pointed star like this is not convex. I'll show you why. Because the definition of convex says if you take any point on the boundary or in the interior of a convex figure and you draw the line that connects those points, that entire line will lie inside the figure. Well, that isn't true if you take a point in a non-convex figure and try to connect it to another point in a non-convex figure. Like when we look at the line that connects those 2 points, you can see some of that line falls outside of the figure. And you can see how that would screw up a formula about the sum of the interior angle measures, because yeah, there's an interior angle measure here and an interior one here and one here. But then there's these big ones here because of this non-convexness, you see, and that would screw up the formula and it doesn't work. That's all I mean by convex. But this should seem a little familiar. Here's one last example of a statement concerning an integer n. The number n factorial, and n factorial, of course, was covered in that lecture that I hope you got a chance to watch over the weekend, is always even when n is greater than or equal to 2. So there are restrictions about for what n these statements concerning the integer n are true. Like this last statement tells us n has to be greater than or equal to 2. This first statement, just the very statement itself, requires that n cannot be smaller than 1. So that would start at n greater than or equal to 1. What about this statement about the interior angle measures of a convex polygon? What's the smallest that n could be for this to actually make any sense geometrically? Well, let's just think. Could we have a convex polygon that had fewer than 3 sides? No, because if you just had 2 sides, it would either just be a single line where the sides are the same side and there's no volume in there, there's no angle in there, or it wouldn't be closed. A polygon's closed up. You know, you can walk around the boundary of it. So this is for n greater than or equal to 3. And this becomes important, that there is going to be some value for n for which these statements concerning an integer n start being true. Okay. Now, I can draw my picture for you. The principle of mathematical induction says something like this. Let's say you've got a statement, P of n, about an integer n. Okay. And the idea is you want to prove that it's true no matter how large n gets. So the idea behind proof by mathematical induction is this. We want to get onto this staircase, and we can imagine these steps as representing the integers for which the statement is true, like n naught could be the lowest level integer for which the statement starts to be true. So the first thing we want to do is we want to prove that we can stand on that bottom step. We want to prove we can get onto the staircase. This is called the basis step, where we actually say, hey, at least this statement is true at some bottom low level value of n. We call that bottom level value n naught. Then what we want to do is this. Assume that if we're standing at step K, so here we are, we're standing on step K. We assume we can stand there. What we wish to prove is that from step K, we can step up and stand on step K plus 1. This process is called the inductive step, where we actually are trying to step up the staircase. Knowing that we're standing on one step, we want to prove that we can step up to the next step. If we do that, folks, think about what it means. It means we can stand on the bottom of the staircase. We've proven that P of n is true at some low level. And then we've proven that no matter what step we're standing on, including right here, we can step up to the next step. That means we can just keep stepping up to the next step. And that means this statement will now always be true, because we've proven that if it's true at some level, it'll always be true at the next level. And so I like to draw my little math angel. She toots her little math horn, you know, and there she is in heaven, mathematical heaven, because this is the stairway to mathematical heaven. That's my idea anyway. So we're going to try to learn how to do this, okay? But there are two pieces of work for us. Get on the staircase by proving a basis step, and prove that if we're on a step, that we can step up to the next step. That's called the inductive step. Okay. So now we're ready for the formal principle, the statement of the principle. It's technically the weak principle of mathematical induction. It's an interesting statement because it's an if-then nested inside an if-then. And we've never seen that before. It's a double nested if-then. Here we go. Let P of n be a statement concerning an integer n. And now we have some ideas about what those statements might look like. If, and it's a big if, okay? We're going to have a compound hypothesis here. We'll write that in a minute. But if some good stuff happens, then we're going to be able to say the statement P of n is true for all integers that are big enough. In other words, n greater than or equal to some bottom level integer, which we call n naught. Folks, we're not going to prove the principle. We're going to invoke the principle. We get to use the principle without proving it. How do we use it? Well, we want the conclusion of it. To get the conclusion, our work is going to be to establish that the hypothesis is satisfied. If we can show we've got the hypothesis satisfied, whatever it turns out to be, then we're going to get the conclusion for free because we get the PMI for free because we don't have to prove it. We assume it's true because it's self-evident. All right, so here is the two-part hypothesis for the principle of mathematical induction, the weak principle. Part one. So it's if P of n naught is true for some integer n naught. So that means we can, stand on the bottom step of the staircase. And here comes part two. For any integer k greater than or equal to n naught, if P of k is true, then P of k plus 1 is true. This part is the part that says, if you can stand on step k, then you can show you can stand on step k plus 1. So if we can show both this is called the basis step, showing P of n naught is true. If we can show that the statement is true at some lowest level, and if we can prove the inductive step, and that inductive step is proving an if-then. We have to prove this if-then. This is the inductive hypothesis. Usually we prove the if-then directly. We'll assume the inductive hypothesis, and then our wish to show is to show this conclusion that P evaluated at k plus 1 is also true. So that's the principle. So what is our work? Our work is very intimately connected to satisfying the two-part hypothesis, okay? If we wish to show or to prove P of n is true for all integers n greater than or equal to, say, some n naught, we must show two things. And those two things are exactly the two parts of the hypothesis. We have to prove P evaluated at n naught is a true statement. And we're going to be very careful about that. We're going to talk about how it's not logically sound to start with an equation that you're trying to establish. And then two would be we're going to assume P of k is true, and then show that forces P of k plus 1 to be true. So we're going to show the if P of k, then P of k plus 1 holds. So when we do this work, then we will invoke the PMI. I don't usually like to write out the principle of mathematical induction. It's tedious, right? It's just too many syllables to write over and over again. So we will shorthand it with the PMI. Invoke the PMI. Step one, P of n naught has to be proven. And then P of k implies P of k plus 1 has to be proven. And then we just invoke the PMI. And that is a statement that says, hey, the statement you're looking at is true for all integers greater than or equal to n naught. Then we can say that P of n is true. for all integers n greater than or equal to n naught. All right, enough of that. Let's think about something that might be useful to actually prove. So a few of you have taken calculus, right? So remember when you do Riemann sums and you're summing up all those teeny tiny skinny rectangles that are under a curve, there are helpful formulas for these kinds of examples, especially if they involve curves that have quadratic components or linear components or cubic components. So here's a useful formula that we're going to actually prove tonight, and it's the sum of the first n positive integers. So the formula says, well, that's the title of it, the sum of the first n positive integers. And the formula goes like this. If you wrote it expanded, if you wanted to expand it out, it would look like 1 plus 2 plus ... Keep going up to plus n. Well, it turns out that sum of those first n positive integers is actually given by the formula n times n plus 1 over 2, where n is that n. Okay. Or it could be written using summation notation, and we'll practice with that tonight in our induction proof because it's just good practice. It's the sum from I equals 1 to n of just the expression I. This is the simplest general term formula that you could possibly have because the formula is just the indexing variable. When I is 1, right, you get the 1. Then I increments to 2, so plus I is 2, so you get the 2. Keep incrementing, plus, 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 and then finally I takes on the value 9, n, excuse me. And so n is that last term in that sum. So this is given by this formula, n times n plus 1 over 2. Okay. By the way, this is the sum of integers, isn't it? Oh, we've got some chat going on. Let's see what's going on with the chat. Oh, good. All right, good. I should have opened that earlier. Sorry about that. It was Ronnie talking about the degrees inside a triangle and a quadrilateral. He knew them. That's great. Okay, thank you, Ronnie. All right, so let's prove this formula. It's very useful. That's going to be our example 1. Prove that the sum from I equals 1 to n of the expression I is equal to n times n plus 1 whole thing over 2 is true for all integers n greater than or equal to 1. Now we are told that we are to prove it for all integers n greater than or equal to 1. We are being told to start at 1. We are being told the value of n naught, okay? So you should be aware of that. You'll always be told where to start. Okay. The other thing to realize is that this is an equation that we're going to be establishing. And an equation has a left-hand side and it has a right-hand side. And one of the things that you probably, we'll call them LHS for obvious reasons and RHS for obvious reasons. One of the things you probably did in high school might have looked a little like this. Let me get my little picture out. This is sort of like my scrap papers today. It's like my board notes today. How many times did you start with the equation that you wanted to prove? Like if you wanted to prove, that x squared minus 7x, I don't know, minus 8 is equal to, I don't know, x minus 8 times x plus 1. Let's say you wanted to try to establish that. How many times would you actually start with that equation? You might start with the equation and then you might multiply this one out, right? But you've already got this one. And then, you might, I don't know, you might add these together. And you'd be like, oh, voila. I got the same thing on both sides. They must be equal. Well, I'm going to just show you a problem, not necessarily a problem with that particular argument, but here is a problematic argument. I can prove 0 equals 1 if I start with 0 equals 1. Watch this. Okay, I prove 0 equals 1. Okay, but first, 0 equals 1. I'm going to prove that's true by this strategy. All right, so I'm going to add 3 to both sides. That's perfectly legal. Now I'm going to multiply both sides by 0. Voila. 0 equals 0. You see the problem with the reasoning? You can't start with the equation that you wish to establish. And this, my friends, is an equation that we're going to try to establish. It's true. It's several different stages in this proof. Okay. So we will never be able to start with the equation we wish to establish. All right. So let me show you how we correctly write this argument. The proof, by the way, in even the most high-level mathematical journals, if a mathematician is writing a proof by mathematical induction, they always tell the reader that. All right, so let's set it up. Let's tell the reader what we're doing. Let P of n be the statement. And now we're going to write the statement one more time. On a test, you could say be the statement above if you're feeling rushed for time. When you're doing your special homework, though, you need to write down the statement as part of your proof, okay? Because nobody prints up the actual paper. All right, so that's the statement. And we've been asked to prove it for n greater than or equal to 1. So here we go. See, the nice thing about induction proofs is they're very methodical. The first thing you do is you write down the statement that you're going to try to prove. Okay, that's done. The next thing you do is you skip a line and you start your basis step. Our basis step always starts the same. Tell your reader what the bottom level integer value is. In other words, identify n naught. So you just say, hey, let n naught equal whatever it is. In this particular example, it's 1, okay? I'll write it in red. Remember, let's go back and look at our principle of mathematical induction. Because we're trying to use that. We're trying to establish the hypothesis. So the first thing we have to do is the basis step. We have to show that P of n naught is true for some integer n naught. So that's what we're working on right now. So we wish to show, it's always the same wish, that P of whatever n naught is, that's different for different problems, but here it's 1, is true. Okay, everybody with me? That's what we're going to do. Now this is P of n right here. This is P of n. The argument is n. See, the argument is this quantity that's inside the parentheses, and it appears here as an upper limit. It appears a couple times on the right. So when we say we wish to prove P of 1, well, we got to figure out what P of 1 actually is. P of 1 is this statement, P of n, except wherever there's an n, instead, we're going to put a 1. Now, we can't write P of 1 as if it's true, but what we can do is work separately on the left-hand side of P of 1 and figure out what the left-hand side of this equation looks like when n is 1. Then we can turn around and evaluate what the right-hand side of this equation turns out to be when n is 1. And hopefully, they'll both turn into the same numbers, and then we could say that those two sides are equal. So the caution here, this is the cautionary tale. We may not prove P of 1 by starting with P of 1. You know, P of 1 is an equation. Okay, this is thinking notes here. We will look separately at the left-hand side of P of 1 and at the right-hand side of P of 1. We will show both sides evaluate to the same value. Once we do all that, then they are therefore equal. Then they are therefore equal. Only then, after we've looked separately at the left-hand side and the right-hand side, folks. Okay, so this is a big thinking notes. All right, let's do it. And I'm going to try to use some color coding. All right, the left-hand side of P of 1. Let's look at that. Left-hand side of P of, I'll put the 1 in red just to emphasize that we're looking at P of 1. All right, so everywhere we see an N, instead put a 1. So it is the sum from I equals 1 to 1 of just the indexing variable I. Well, that's just a single term when I takes on the value 1. I mean, that's all it is. It's just 1. Great. So the left-hand side of P of 1 is just 1. Let's look at the right-hand side. When n is replaced by a 1, the right-hand side of P of 1 is, well, 1 times 1, putting the n equals 1 in there, plus 1 over 2. Of course, that's 1 times 2 over 2, and that's also 1. Yay! The left-hand side and the right-hand side, when evaluated separately, turned out to equal the same value. So we can just say, hey, since the left-hand side equals the right-hand side, P of 1 is true, and we have just gotten ourselves on to the bottom step of the staircase. We are standing here. Okay. Now the next thing we're going to do is stand on step K and prove that we can climb up to step K plus 1. That is called the inductive step. Skip a line, label it so that your reader knows we're moving on. Okay, so the inductive step. Now, the inductive steps start the same way in every proof. You tell the reader what value k, which is an integer, and you tell them that too, starts at. So here, I'll just show you how to write it. Let k greater than or equal to, and what you put here is in naught, because that's, we've got to be able to get off this step. If k couldn't be this step, we could never get off the bottom step to get up here to, to a higher k. So k has to include the possibility of equaling in naught. So let k greater than or equal to n naught be some integer. Now let's just remember what the principle says. It says, for any integer k greater than or equal to n naught, if p of k is true, then p of k plus 1 is true. So it's an if-then we're proving, folks. We're going to assume the inductive hypothesis. We're going to assume p of k is true, okay? And then we're going to show that that forces p of k plus 1 to follow. So here we go. They all kind of look the same. Assume p of, I'll put it in red just to emphasize here, k, the argument is changed to k, is true. But we're going to be more specific, i.e. assume, let's just state p of k, okay? Here's p of n. Everywhere we see an n, we're going to replace it with a k. So it's the sum from I equals 1 to k of I equals k times the quantity k plus 1 instead of n plus 1 over 2. This is our inductive hypothesis. This is our proof money. This is what we are assuming. So I'm going to use our proof money symbol to remind us, hey, this is the money in the bank that we're going to use. It is called the inductive hypothesis. This was worth noting here in the margin just for the notes. All right, now, what do we wish? We want to step up the ladder. We want to step up the staircase. So we wish to show p of k plus 1 is true, i.e., we wish to show, and now we can write p of k plus 1. It's the sum from I equals 1 to k plus 1 of I equals, well, now we got to use parentheses because we're putting in k plus 1, where there used to be a monomial, n or k, and then k plus 1 is the other factor, holding over 2. That's our wish. And in fact, so that I don't mistake the wish for the proof money, I'm actually going to kind of put it like a dreamy wish cloud around it, just because my eye will settle down on the wrong thing and I'll accidentally assume this when I can't. So this just keeps me visually sorted. This is our money. This is our wish. So how do we achieve the wish? Let's see. Well, we can't start with this equation because that's what we wish to prove. But we can start with one side of the equation, work on it, rewrite it using legal algebra, use substitution, use our inductive hypothesis if we're clever enough to figure out how to do it, do some more algebra, and turn it into this. And that's our strategy, folks. Start with the left-hand side of p of k plus 1, work on it until it looks like the right-hand side of p of k plus 1. And we're going to keep this where we can see it because we got to keep our eye on the prize. You can't do this blind. You have to know what you're headed for. These proofs, you have to know what you're trying to do or you'll never, manage it. All right, so we're trying to prove this. So starting with, tell your reader, we're going to start with the left-hand side of p of k plus 1, because this is p of k plus 1. Starting with the left-hand side. of P of K plus 1, we have, so we're going to start with this, the sum from I equals 1 to K plus 1 of I. Now we are going to try to change this into that. Okay? Well, we learned a trick at the beginning of class today, and that trick was breaking off the last term of a sum. So let's apply that trick here. Let's rewrite this as a sum of two sums where we break off the last term. In other words, the term where I goes from K plus 1 to K plus 1. We can break that one off and look what it leaves behind. Look at this term. Why would we do this, folks? Why would we make this algebra step? Well, look at our money. Look at what we have in our hand as hypothesis. Don't we know something about the sum from I equals 1 to K of I? We do. We know it's equal to this because this was what we assumed to be true. This was our induction hypothesis, you see. So we make this algebra trick because we realize, hey, I'm putting green boxes around it to kind of remind you, we can make this substitution using the inductive hypothesis. And when we do make this inductive hypothesis substitution, we say so. This is by the inductive hypothesis, or you could say by induction. But no matter how you decide to say it, by induction or by the inductive hypothesis, you tell your reader exactly when you make that substitution. It's good etiquette. We're substituting in K times K plus 1 over 2, which is the right-hand side of P of K, for the left-hand side of P of K, which is what we assumed is true. We know these two sides are equal because this was our inductive hypothesis. That's where that substitution happens. And then we are set to kind of take stock and see where we're at and can try to continue to get closer to what we're trying to reach. We're trying to get this. We're trying to get K plus 1 times K plus 2 over 2. We started with this sum. There it is. All right, so let's look at let's take stock. See where we're at right now? That is better than that. I mean, this looks closer to K plus 1 times K plus 2 over 2 than we had at the beginning, but we're still not quite there. But let's see if we can get a little further along the way here. Well, we evaluate this. We can drop the summation symbol because this is just the single term where I equals K plus 1. Great. So now we're looking like that. That's even closer to looking like this. But notice the differences. This is the sum of two terms. One of them is a fraction over 2, but the other one is not. What we're shooting for is a single fraction over 2. So what could we do to get from here closer to that? Any ideas?
Multiply K plus 1 with 2 over 2.
That's right. Multiply K plus 1 times 2 over 2 so that we get a common denominator. Very nice. So we've got K times K plus 1 is already over 2. But if we multiply 2 times K plus 1 here, we can put it over 2. And now we're just a step away from getting this desired expression, right? You can factor the K plus 1 out to the right if you like, and then out comes the K plus 2. And now we can just rearrange these factors up top. And we've got k plus 1 and k plus 2, of course, we can write as k plus 1 plus 1. We know it's k plus 1 plus 1, but k plus 2. And this, my friends, which is the right-hand side of p of k plus 1. So we started, remember what we started with? We started with the left-hand side of p of k plus 1. It looked like that. We did the break off the last term of the sum trick. We used the inductive hypothesis, what we assumed p of k was true, and made this substitution. We did a little algebra, evaluated this broken off term, did a little more algebra, all knowing that this was what we were shooting for, keeping our eye on the prize the whole time. Not quite done. We have to invoke the PMI, folks. It's not complete until we invoke the PMI in order to get what we really wanted, which was that this is true no matter how big n gets. So by the PMI, we can now say that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2 is true for all integers n greater than or equal to 1. We started at 1. And that's the end of the proof. So we've just proven this formula. Let's work on applying the formula. Let's do a little application problem before we break. And one way to think about this formula is in expanded form. 1 plus 2 plus dot, dot, dot plus n is equal to n times n plus 1 over 2. Okay? You can think about it that way. So example 2. Use the formula to evaluate, where this is the formula. One plus 2 plus 3 plus dot, dot, dot plus 1,000. So let's see if we can use the formula. This one's real easy. Super, super simple. So example 2, solution. N is 1,000, right? The n is 1,000. So 1 plus 2 plus dot, dot, dot plus 1,000, according to the formula, is equal to 1,000 times 1,001, right? N plus 1 over 2. What is that? 500 times 1,001. That's 500,500. So it's super easy to use the formula if the little exercise is given in such a straightforward manner. But of course, we want to make it more interesting. Let's try another one. Evaluate. Again, just recall our formula because I'm getting ready to disappear. Well, or disappear it. It's this is written in summation notation. That's our formula. Okay. Written using summation notation. You can write it either way. Okay. Evaluate. Here we go. 5 plus 10 plus 15 plus dot, dot, dot plus 5,000. So listen, the formula needs to see a 1 plus 2 plus 3, right? It needs to see, it starts at 1. It increments by 1. It doesn't increment by 5. It's 1 plus 2 plus 3 plus dot, 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 plus n. So what do you think we can do here so that we can attack this? Any ideas?
Multiply it by 5.
What's the opposite of multiplying? Well, I don't want to multiply everything by 5. I want to take a 5 out of everything, right?
Oh, yeah, divide.
Factor it out. Yeah. Factor it. Yeah. So let's take out a 5. 5 comes out of 5 and leaves a 1. Comes out of 10 and leaves a 2 behind. Comes out of a 15 and leaves a 3. And there we have it. Don't forget to multiply your answer by 5. But see, now this is the sum from 1 to 1,000. Well, we already just did that. It turned out to be 500,500. So whatever that equals, you can put that in your calculator. I don't care. That's the idea. I do want to give you a do later. So I want you to think about this just a little bit more. I'm going to give you a hint. The hint is that the sum from I equals 1 to n of a sub I minus the sum from I equals 1 to j of a sub I is actually equal to the sum from I equals j plus 1 to n of a sub I. And this is where 1 is less than j is less than n. So j is between 1 and n. So you can see why this is true. If you bring this over to the other side, this is just a single sum that would be written as the sum from 1 to j plus the sum from j plus 1 to n. If you pull this over to the other side, it's just a very small step beyond breaking off the last term. It's sort of like just cutting the sum in the middle somewhere between j and j plus 1. All right, so keeping that in mind, you can do this example 4. Evaluate. 621 plus 622 plus 623 plus 624 plus dot, 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 plus 6,000. I like my thousands. I like to think in thousands. Okay. And that'll give you some good practice using the formula. And when we reconvene, we'll continue with induction. And finish your homework that's due Wednesday, and I'll get as much to you over the next few days as I humanly can. It's been extremely challenging. Between my computer dying twice in a period of 2 weeks to having to make tests and then grade, and it's just been just a little bit much. So lucky you, it gives you just a tiny bit of a little breather right now. If you've got other courses that need your full attention, you're getting a tiny bit of a little breather in this class, and I'm sure that you like that, no doubt. So, any questions? No? All right, so our next office hour is Wednesday, and I'll have something in front of you that's interesting before then, something that you can look at and come ask about, I promise. It'll be on 5-2, next special homework, maybe the video, mini special homework. Let me just get through the next 24 hours, okay? It's just been crazy. All right. Thanks for playing. I'll stick around in case anybody's got any questions.